Hello everyone and welcome to the first lecture of MA 501 Engineering Mathematics. So where I'd like to start off is right in the title of the course, Engineering Mathematics. And mathematics is the study of a collection of human knowledge obtained over the years in many different areas of the mathematical sciences. The engineering in the title, Engineering Mathematics, involves a very specific subset of mathematics known as applied mathematics. And if you've ever taken, hopefully you have the prerequisites for the course, a basic course in calculus, linear algebra, or differential equations, you'll definitely have seen the solution and the solution methods present in various aspects in the beginnings of applied mathematics. In this course, our goal is to delve a little bit deeper and get a deeper understanding of this subject matter as a whole, and prepare you for more advanced engineering problems and advanced engineering methods that you'll encounter throughout your studies and your career. So we'll begin our class with a brief historical introduction as to how this all came about, and essentially why it is that we'll be starting where we're starting. So we'll begin our studies with a brief historical introduction into where it is we'll be starting, and then work from there to develop some of the basic ideas of the course a little bit later on in the lecture. And the main person that we have to focus on here is René Descartes. This took place in the mid-17th century. And his introduction was an introduction of what was called analytic geometry. And the idea of using coordinate systems to study things in geometry, study problems, and get a better understanding of certain problems of geometry and other applied problems. And what came about, especially in terms of the application to physics, was the need for an independence of coordinate frames. What this means, very simply, is that if you're going to study a problem in geometry, in physics, in an applied problem, the solution that you find should not depend on a chosen coordinate system or chosen coordinate frame. And if it does depend on that coordinate frame, for instance, if I were to do an experiment in one coordinate system and then do the same experiment in a different coordinate system and I get two different results, there would be, in some sense, a big problem there, some sort of problem. So we need some sort of invariance and independence if we're going to switch between coordinate frames. And the main idea behind this is that we need to think of entities, like physical entities, as they are. So if you're going to talk about force, if you're going to talk about the electric field, the magnetic field, things like charge, current, these things should not depend on the chosen coordinate system. So the idea of coordinate frames is very helpful, but we need some sort of new language as well that is hopefully in some sense independent from these coordinate frames, and the coordinate systems allow us to evaluate certain quantities. They're sort of like our toolbox for evaluating certain physical quantities when the time comes to actually evaluate them. But we need these physical quantities to be independently described outside of the chosen coordinate system. And this is the start of essentially what's called vector tensor calculus. And this gives us a description of essentially all things that you can think of in modern physics, modern engineering, that is essentially coordinate free. It doesn't depend on the chosen coordinate system, and the relationships don't depend on the chosen coordinate system. However, you can use individual coordinate systems, the most conveniently chosen one, to solve or find out information about the solution to a specific problem. One of the nice things about vector tensor calculus, in the vector tensor concept in general, is that it allows for a very compact form of equations. So equations are very, very compact. So, for example, one of the most famous equations that I would argue that most of you have seen before, or at least familiar with, is the equation used by Einstein to express the relationship between a unit of mass and a unit of energy. It equates the concept of mass and energy. And this can be rigorously investigated and shown using this vector tensor concept and using Einstein's general theory and special theories of relativity. These, by the way, are a very, very shining example of the power of vector tensor calculus. Einstein's general theory of relativity, which is the general theory of gravity, and his special theory of relativity, which is the theory absent of motion, absent an accelerating body, or absent of a gravitational field. So the main idea here is that we want to think of coordinate systems as the technical tools that we'll be using, but the vector tensor concept here, there are actually no coordinates. This is independent of coordinates. And the starting point here is going to be vector algebra, and then we're going to move on to the vector calculus. So in the book, right, you get an introduction to vector algebra. In chapter 6, specifically 6.1 to 6.4. This is the dot product and the cross product. For vectors in 3D. And you're going to want to review that and at least be familiar with that material going forward. And it will definitely use that as we get to the middle of our lecture today, because it'll become very, very important. This is serves as a nice introduction to sort of where we're starting and the starting point that we're going to take off from for this course. So the vector concept contains the following three main objects, and really it's only one main object. This is scalars, vectors, and tensors. Bring this down to one line below. And you will hopefully already at least a little bit familiar with the first two objects here, the scalar and the vector. But the idea is that we have a number of different ways mathematically to represent physical properties and physical things that are going on, say in a physical system. This does not mean that this concept can't also be applied to other areas and to solving problems in other areas outside of physics. There are many different possible applications of this concept, but the main idea here is that physically we can describe things in terms of scalars, vectors, and tensors. A scalar, or this is why we can think of these as actual examples of tensors. A scalar is what's called a rank 0 tensor. A vector is called a rank 1 tensor. And there are actually tensors of arbitrarily high rank. So you can go to, in general, talking about a rank n tensor. So, you can go very deep in terms of how you define what exactly mathematically a tensor is, but we won't be doing that in this course. In this course, we'll just be thinking of a tensor as some sort of physical object, and a physical object that in certain ways is invariant with respect to the coordinate system that it's in. So it doesn't depend on what coordinate system you choose to describe it in. In order to define it in any more advanced way than that, it's a little bit difficult. So we're not going to be going through and doing that, but rest assured that it can be done. So the idea is that in terms of basic examples here, I'll give some tensor examples in a little bit, higher order tensors. But for scalars, you could have, say, I guess really what we should say is, scalars are in some sense like numbers. Right? So they really just have one property. They have a magnitude. A vector is something that has a magnitude. And a direction. And then tensors are something that has, more properties. They transform in a very special way. So I actually won't even include that. I guess I'll change this numbers here to just a magnitude. A scalar is a quantity with only a magnitude. A vector is something with a magnitude and a direction associated with it. And a tensor is something that is even more, has more things associated with it. And specifically, it has to do with how it transforms under a certain coordinate transformation. So it transforms is invariant under coordinate transformations. So really what we're concerned with in this class, in the first part of this course, is going to be vector calculus, which deals with functions of these scalar functions, vector functions, and tensor functions. So this is actually what we call a scalar field. So for instance, a scalar field is a scalar valued function a vector field is a vector valued function and we can also have a tensor field, a higher order tensor field, this is a tensor valued function. So the idea here is that these are the all of the basic ways that we can describe things in physics and basic engineering. Now, like I said, we're not going to be focusing too much on tensors or higher order tensors. We'll just be focusing on scalars and vectors for the first half of this course. But the idea is that, for examples of a scalar field, you could talk about the temperature field. Right, the temperature is a function of position and time. Right, and so this is an example of a scalar field. That every single position, or if you have a given coordinate system, where your spatial coordinates are x, y, and z, and your time is time t, the temperature at point x, y, z, time t, can be viewed as a function of x, y, and z, x, y, z, and t. For instance, in Chicago it might be 30 degrees, but in Boston it might be 50 degrees. All right, so this is an example of of a very common scalar function. Another great example of a scalar field would be the pressure field. Right, let's say you put some force on two sides of a metal plate, and you change the force on the boundaries of the plate. Is going to change the pressure at every point inside the plate. And possibly, if you change it quick enough, that pressure field could also correspond to the propagation of a wave, or the magnitude of a wave. Which is very often said to be like u of x, y, z, and t in 3D plus time. So in terms of 3D plus time, it's a little bit hard to visualize. It's even hard to visualize in 3D in general, but it's best viewed, the concept of a scalar field is best viewed if we view it with just two variables, so a static plot. So this right here is a nice little picture showing exactly what we mean by a scalar field in 2D. You have an x-axis, say, and a y-axis, and this could be, say, maybe the static temperature distribution or the static pressure distribution at a given point in two-dimensional space, where the color here is indicating the value of the scalar field. So you say that maybe the temperature is going from negative 3.382 degrees Celsius to positive 0.459 degrees Celsius. Right? You can see very, very clearly how important this is in terms of modeling. We want to be very, very clever in understanding the mathematics underlying this right here, and it sure seems like vector calculus, and specifically you'll probably have seen this concept in multivariable calculus course, is going to be very, very important for us going forward. For other examples, like the wave potential and the temperature field, can depend on time. So let's look at how that could potentially happen. Right? If you say heat up a metal plate in the middle of the metal plate in a certain pattern, right? As time goes on, that heat and the temperature is going to flow throughout the plate. So this is an example of the solution to the heat equation over a certain time period, and you see that initially, so over the entire time, it's a function of two variables of space, x and y, and time as well, because at an initial time t, it's very sharp. So you put the temperature at a certain value on this shape right here, and then as time goes on, the heat just kind of flows out uniformly and smooths out. That's actually a characteristic of the solution to the multidimensional heat equation which is what's called a partial differential equation, which is a very, very common thing in mathematics and in physics and applied mathematics, and results directly from certain physical laws that are expressed through vector and tensor equations. As another example, you could consider the motion of a wave in a 2D membrane. If you ever take a really thin elastic membrane and you strike one portion of the membrane and you want to study how the waves travel throughout the material. This is where my research is focused in, and this is a basic kind of animation here showing what would resulting wave propagation in some elastic membrane. Right, you see that you kind of give it some sort of initial strike with certain boundary conditions, the waves will reflect off one another, reflect off the sides, and continue to kind of go forth. And what's plotted here is the wave function as a function of two spatial variables and the time variable as well. It's sort of like an animation. The idea here is that these scalar functions are the province of multivariable calculus and very, very useful for describing the physical world, but it turns out that what's more useful for describing the world is the concept of vectors and tensors. So I'll give you an example of some vector fields and some vectors now. So a great example of a vector field is the electromagnetic field, where the electric field vector is denoted E typically, and in general it's a function of 3 dimensions and time, and we call the magnetic field vector B, and it is also a function of x, y, z, and time. As another example, you consider the fluid flow field. If you have like fluid, in fluid dynamics, is the fluid flow velocity field, where at every given point you can talk about the flow velocity or the flow speed is very often called, say, like u, vector u of x, y, z, and t. It's a function of position and time in general. And the reason that both of these are good examples of vector fields and not scalar fields is because, as you can see from this picture of the field lines for a magnet, right, at each given point, there's, for a magnetic field as well as the electric field, there's both a magnitude and a direction that's needed to specify the total effect of the field at that point. So we know that the magnetic field lines flow from north to south. So if we were to, say, describe this with an object mathematically, a scalar field doesn't suffice. At every given point, we need to specify the magnitude and direction of this magnetic field. Likewise, for fluid flow, say fluid flow around an airfoil, if you have some sort of airfoil right here, and then you have a fluid flowing in a certain direction, in this case from left to right, at every given point, the fluid has a different velocity. Like here, the velocity of the fluid is very slow, and it's generally in this direction, whereas at this point, the velocity is very, very quick, going over the top here, and you can see that it's pointing in a different direction. At any given point here, the velocity field of the fluid flow is different in terms of both its magnitude and its direction. This is why we need vector fields to describe both of these phenomena. So just for our picture here, a vector field, we have just a 2D vector field that is, very it could very easily be a charge field, or an electric charge field, or a magnetic field, even going around a coiled system of wires, where the magnetic field kind of goes like this. It goes through the coiled system and up and around in each given direction. So this could really even be a cross section of a magnetic field in three-dimensional space, just visualized in 2D. It's important to emphasize that these are not the only examples of vector fields and scalar fields, but these are some of the more common ones that you'll see. But it turns out that there are many, many other very important examples of all types of fields, and even tensor fields, as we'll see. So let's try and kind of summarize this and mathematically pin down exactly what one of these fields is. So we'll let X be an element in some set X, capital X, and X is the independent variable. And we're going to put here an S in parentheses, because it could also be, if X is a vector, it could be a set of variables. And I'll say that Y is an element of some set Y, which we call the dependent variables. Now, being intentionally vague here, X could be a vector, it could be a tensor, it could be just a scalar, a normal scalar, the so-called domain. This set right here, X, we'll call the domain of some function. And the set right here we'll call the range of some function. And we'll introduce explicitly some function or sometimes called a functional relationship between Y and X. Now remember, it's important to remember that X here is the dependent variable. It could be a vector, it could be a tensor, it could be a scalar, and same thing with Y. Depending on what these relative quantities are, we get different types of mappings. If both of them are tensors, then it's very, very relatively complicated. But if both of them are scalars, then we're in the realm of single variable calculus. But the main idea here is that this function, f of x, is a mapping of the domain x onto the range y. So this gives us the set of, we'll say, 9 possible submappings. Where we'll distinguish between the domain, what that is, and the range, what that is. So if the domain, is a scalar or an order 0 tensor, the domain variables could be a set of vector, or it could be a vector, which means it's a set of values. Remember, a vector is just an order 1 tensor. And we'll just put higher order tensor. X could also be a higher order tensor. So rank 2 tensor, rank 3 tensor, so on and so forth. And just like the independent variable, the dependent variable could also be any one of these things. So we just want to give a brief description of what each one of these objects is and kind of where we're starting in this course, and what we'll end up generalizing to in this course. So if f is a function from a scalar to a scalar, this is the realm of scalar functions of scalar variables. So scalar functions, or scalar valued function, of scalar valued independent variables. This is the realm of calculus 1, so single variable calculus. I wouldn't just say calculus 1, but probably calculus 1, calculus 2, and calculus 3 in the WPI model. So calc 1 deals with differentiation, calc 2 with integration, and calc 3 at WPI deals with sequences and series, and specifically culminates in talking about Taylor series expansions. So this is essentially a scalar valued function of a scalar valued variable. If the domain is a vector, and it's going to a scalar valued function of a vector valued variable, this is the realm of multivariable calculus. So it's a scalar valued function of a vector valued variable. So for instance, like the temperature function, the scalar fields that I introduced before. This is typically talked about in Calc 4 at WPI, or any multivariable calculus course. For a scalar value or a vector valued function, of a scalar valued variable. This is what we call a parametric curve. And this is essentially, I'm going to highlight this in red because this is what chapter 11 is about, and we'll be starting our course. Because it provides the most straightforward extension and discussion of how to deal with certain operations and extend certain operations from calculus 1, 2, and 3 to more complicated mappings. What we'll then move on to is vector-valued functions. Of a vector-valued independent variable. And depending on where you took your multivariable calculus course, you might have seen some of this, but essentially this is where we'll move into. And this is the main focus of chapter 12, and also where all of our vector field stuff can be found. Now, for the higher ordered case, I'm not going to go through and talk about that too much right now, but I might give an example in a little bit of some higher ordered tensor functions and where you might see higher ordered tensor functions in terms of applications. So we'll just pick one of those previous examples and we'll actually show how, depending on how complicated we're getting in and how complicated we want to model in terms of a certain physical situation, we could have really a combination of all these types of mappings. So the first example that I want to consider is we'll consider Maxwell's equations. For dielectrics. And the idea here is that, well, we've already seen that the electric field and the magnetic field throughout a given material are vector fields. And it turns out that you can go through and actually derive, which we'll do later on in this course, if we have time, using some vector calculus. You can derive very, very nice equations that govern the electric field and magnetic field. And also, if the electric field and magnetic field are moving through some material with possibly very complicated material properties, it turns out we also have to introduce two other vector fields. It's called the electric displacement field. It's denoted as D, typically. And it's called the magnetization field. It's denoted as H. There are two other corollary fields that are associated with the electric field and magnetic field, but through material with possibly very different material properties at every given point. And these are all governed by what are called Maxwell's equations through dielectric media. Specifically, I'm not going to write I'll just kind of show you an image of what each one of Maxwell's equations look like, and I'll also include the name of each individual Maxwell's equations. So this first equation is called Gauss's law. The second equation is called Gauss's law for magnetism. The third equation is called the Maxwell-Faraday equation, or Faraday's law of induction. And the fourth Maxwell equation is called Ampere's circuital law with Maxwell's addition. And these four equations govern how the electric field, the magnetic field, the displacement field, and the magnetization field all evolve with respect to time and space in a given medium. So these can all be derived using basic laws of physics and some basic vector calculus. But the main idea here, and again, these operations might not be familiar to you right now, but rest assured they'll be familiar by the end of the first half of this course. They all have physical meaning attached to them, but they're a mathematical expression of basic physical laws. We also have a connection between the electric field and the displacement field, and the magnetic field and the magnetization field, that are called constitutive relationships, or constitutive relations. And these relations take the following shape. Basically says that the displacement field is equal to a tensor, second order tensor, and this is the dot product with the electric field, and we also have that the magnetic field, B, is equal to the dot product of this second order tensor with the magnetization field, H. Now, for a material that is isotropic, right, and constant, doesn't depend on the relationship between D and E doesn't depend on direction. These two tensors, by the way, this epsilon tensor is called the permittivity tensor. Or the electric permittivity tensor. And this tensor right here is called the permeability tensor. So for material that is isotropic or not direction dependent, have scalar function value. These tensors are really just scalar functions. Or the constitutive tensors. but for material that has a dependence between D and E and B and H depends on direction, or an anisotropic material, these constitutive relations are in general tensor relations, and these are specifically rank 2 tensors. For the constitutive tensors. So the idea is that if you're not careful, for a more complicated material, you run into very severe mathematical issues, and you have to be very careful how you're mathematically describing something. But this is just one sort of overview, right, of where these considerations are very important. Next example that I'll talk about is going to be the idea of elasticity, or the vibrations of an elastic bar. Also sometimes known as solid mechanics. And with solid mechanics, I'm not even going to write down the general partial differential equations that govern the displacement of elastic motion, because they're actually a lot more complicated than the rules for electromagnetism. But even in elasticity or solid mechanics, we end up having constitutive laws and constitutive relationships that we have to write down. And we'll just go to first the 1D example. I consider motion of a mass on a spring. Spring constant K. Well, you know from basic Newton's law that the force of the spring, and this is not Newton's law but Hooke's law, the force generated by this spring is going to be negative K times X, where X is the displacement of the mass from equilibrium and K is the spring constant. And so this is an example of a constitutive law in 1D in solid mechanics. Now, solid mechanics is more interested in, kind of generalizing this idea, generalizing Hooke's law. And this is exactly what happens. We'll say, in 3D, or a 3D solid body, you consider what happens and the relationship between stress and strain in the body, stresses and strain. Well, at any given point inside the body, you have individual stresses or forces in each individual direction, and you also have torsional forces, or rotational forces, as well as rotational stretches that you can do about any of the various axes of the body. So in order to correctly describe this in 3D, you have to consider what's called the stress tensor, typically noted as sigma. And the strain tensor, which is called this E, 2 lines under it. And it turns out that Hooke's law actually does generalize very nicely using something called the double dot product, where sigma ends up being equal to negative C, which is a fourth order tensor, double dot product with the strain tensor. And I'm not going to get into mathematically exactly what this means and how to compute this. And I doubt that we will really focus on it too much in this course, but it's a great example of how you can use vector calculus and tensor calculus very often to generalize one-dimensional relationships. Right. So this is saying that the rank 2 stress tensor for a given elastic body is going to be negative this fourth order tensor and some sort of very special multiplication with the strain tensor. It's almost a direct generalization of Hooke's law in 1D, but instead of using scalar valued functions, we now have tensor functions that obey the law itself. So this should hopefully serve as a nice sort of just kind of like example of how we can very compactly write these equations and these relationships, even very complicated multi-dimensional relationships, in this vector language. But this will conclude the introductory lecture, and I hope I was able to kind of provide some motivation and give you some sorts of the reason, or an introduction to the reason why we're going to be developing this nice language of vector calculus to use in the coming weeks. Please let me know if you have any questions, and have a great day.